Let's consider gravitational fields. Right, various things we need to consider before we start looking at calculations. So, this is a really key point. All masses have a gravitational field around them. So very often we talk about the gravitational field of planets and stars and moons, and that's great, but any mass has a gravitational field, so that's quite important. So if we are talking about a large object, for example, a planet, then we are usually considering a radial field, and all these arrows will point towards the center of the object. So these are to indicate the direction of the force experienced by a mass. So if we have a moon or a satellite or indeed a person stood on the surface of the planet, then they will experience an attractive force towards the center. And this is one of the key features of gravitational fields. It is only attractive. There is no such thing as a repulsive gravitational field. However, if we consider a situation over short distances on a much smaller scale, then we would assume the field to be uniform. So these lines are totally arbitrary, and they just remind us that there is an invisible force field there with a particular direction. So we have gravitational field strength. So you should be very familiar with little g. You will have seen this at GCSE and also earlier on in A-level. And very often we consider this as the acceleration due to gravity, which is 9.81 meters per second squared. So within this context of gravitational fields, we call it gravitational field strength. So it's the same value, 9.81, but the units have changed. Now we can show that the units of newtons per kilogram are the same as meters per second squared, and that might be an exam question. But where do these come from? So we know from GCSE that W is equal to mg. So if you make g the subject, then we have weight over mass, and weight is a force, force over mass. So that gives us the definition of gravitational field strength. It's the force per unit mass. So this is quite useful. So if I know that it's 9.81 newtons per kilogram, what that means is if I place a mass of 1 kilogram in the Earth's in the Earth's gravitational field, then the force it will experience at the surface is 9.81 newtons. However, if we go to another planet, for example, Jupiter, then as expected, it's got a larger gravitational field because of its larger mass. So the same mass, 1 kilogram, will experience a larger force, in this case, approximately 25 newtons. The next thing we need to consider is Newton's law of gravitation. So this is really important. We need to know the definition and we need to be confident with the formula. And you are given this formula in the formula booklet. So the definition, so we have two masses. So we've got any two masses. Sometimes we add this word point, which means we're not going to worry about the varying density. We'll just assume that all the mass acts at a point. So they attract each other. So this is related to Newton's third law with a force that is proportional to each of their masses. So the force is equal to m1 multiplied by m2, or proportional to that there on the top, and inversely proportional to the square of the distance between them. So we're dividing by r squared. Now we've got to be careful here because r suggests that's a radius, and it could be a radius if we have an object on the radius or the surface of a planet, but it's actually the distance between their center of masses, and that's given the symbol r. So just watch out for that. It's not necessarily the radius, it's the distance between the centers. Okay, so we have, this is our general relationship. We have a constant of proportionality, which we are given in the formula booklet. This is big G, not to be confused with little g. There is a relationship between the two, as we'll see on the next slide. The negative sign we can effectively ignore. Now, we will look at that later on this topic and where it comes from and how it's related to gravitational potential. But normally we're looking at the magnitude of the force, so we tend not to include that in our calculations. Okay, so you must know the definition and you must be familiar with this formula. So let's look at calculation. This is your standard 2, possibly 3 mark calculation in the exam. What is the gravitational force of attraction between, for example here, the moon and the earth? So a very typical scenario. So we need the mass of the earth, we need the mass of the moon. We will be given these in the question. And we can call either one of these m1 or m2, it doesn't matter. And we're given the distance, which we assume is the distance between the center of masses, which is r. Now, it might be a different distance where we have to take into account the radius. So if it's the distance between the surface of the moon and the surface of the Earth, then we might need to consider adding the radius. But normally it will be the distance between the centers. So the first thing we do is substitute into this formula here. So we've got G, big G. We can ignore the minus sign. So just multiply by the masses and divide by the distance squared. And we get this very large number here. So expect to get really massive values of force. So 10 to the power lots. And that's what we would expect. So this would be a typical 2-mark question. So we said there is a relationship between little g and big G, and this is how we derive it. So really important to realize that the weight, which we're very familiar with, mg, and this new expression here, Newton's law of gravitation, the force due to that, they're one and the same thing. So we don't have a weight, oh, and also we have a gravitational force. This is just another way of thinking about it. So if we have a satellite, for example, in orbit, then its weight is the gravitational force of attraction. So mg is equal to big G m1 m2 over r squared. So we can see that one of those masses is going to cancel, and the mass will be the mass of the smaller object. So we could call that a little m, and on the left-hand side, that's just m. So that will cancel, and we will end up with a simplified version. We can include the minus if we want to, but we normally ignore that in our answer. And the remaining mass is m2, which will be the larger mass. So very often this is written as capital M to remind us that's the bigger mass. That's normally the mass of the planet. So again, we can do a calculation here. So calculate a value for little g at the surface of the Earth. So we're given the radius of the Earth, we're given big G, and we're given a value of the mass of the Earth, in this case to 4 sig figs. So we can put the numbers into the formula. So we've got big G, we've got the mass, big M, divided by the radius in this case. So in this case, the distance between the center of the masses will be the radius. But we need to be careful with that, because if there's a height, we would need to add that on. But in this case, this is at the surface of the Earth, so it's actually the radius. Watch out for kilometers. This is a really common mistake. It's very tempting to just write 6371, but in this case, we've got times 10 to the 6, because we've got kilometers. So all of this is times 10 to the 6, and then squared. 9.83 newtons per kilogram sounds about right. And that would be the answer in this case.